You probably got this tidy picture, right?
Mm-hmm.
A nucleus in the middle, electrons whizzing around like planets in a mini solar system.
Yeah, simple, predictable paths, a convenient picture.
But ultimately pretty misleading, I gather.
It works for basic introduction, maybe, but the real story, well,
Exactly. Because the real story, the quantum story, is just so much stranger.
definitely.
Those electrons aren't really on fixed orbits at all. They exist as this sort of probabilistic cloud.
That's right, a cloud of probability. You can't pinpoint exactly where one is.
Only where it's, likely to be found.
It's a fundamental shift. Probabilities, not certainties. That's the quantum way.
And here's where it gets really wild, at least for me. The energy of that fuzzy electron cloud. It isn't some constant, steady number.
No, not at all.
It's fundamentally dynamic. It's constantly fluctuating, jittering, never truly stable, which feels incredibly counterintuitive. Why would that even happen?
Well, it's not a bug, it's a feature. It's a core aspect of the quantum world.
A consequence of the basic rules.
Exactly. These fluctuations are a direct consequence of how things work at the smallest scales.
So today, we're taking a deep dive into this really surprising phenomenon. We're using a stack of fascinating sources. One of you shared some articles, research papers.
Good stuff.
And our mission is basically to understand why the energy of an electron cloud is always fluctuating, and maybe even more importantly, what measurable real-world impacts these constant, subtle jitters actually have.
Because they do have impacts. As quiet as these fluctuations might seem, their effects, well, they resonate throughout the physical world.
Okay, let's unpack the why first.
Yeah.
You mentioned quantum mechanics is behind it. Can you break that down a bit?
Sure. At the most basic level, it really traces back to the Heisenberg Uncertainty Principle.
Ah, okay. The one about position and momentum.
Well, yes, but it also applies to other pairs of variables, like energy and time. It tells us you can't perfectly know both the exact energy of a system and the exact time interval for which it holds that energy, not simultaneously.
Okay, so there's always a bit of fuzziness.
Exactly. And this inherent uncertainty allows for temporary deviations from the expected energy. You can, in a sense, borrow energy.
Borrow energy? From where? Just thin air?
From the vacuum, actually. Precisely. This principle gives rise to what we call vacuum fluctuations.
So empty space isn't really empty.
Not in the quantum sense. What we classically think of as a perfect vacuum is anything but empty. It's more like a seething, energetic froth.
A froth. Of what?
Of transient particles. We call them virtual particles.
Virtual. Like, not real.
Well, they exist for incredibly short periods. Pairs of electrons and their antiparticles, positrons, or maybe virtual photons, they pop into existence.
And then vanish again.
Right. Annihilating each other almost instantly. They exist just long enough to be consistent with the uncertainty principle, then they're gone.
Okay, wow. So you have this electron cloud, this probability region, and it's sitting in this constant invisible storm of virtual particles popping in and out.
Mm-hmm.
How does that affect the electron cloud's energy?
Well, the cloud is constantly interacting with this dynamic quantum vacuum. It's not isolated.
It feels the storm.
You could say that. It's absorbing and re-emitting these virtual photons continuously. This ceaseless exchange, these tiny little pushes and pulls from the vacuum's activity, they perturb the electron's energy state.
Ah, so that's the jitter.
It causes its energy to constantly fluctuate around an average value, yeah. And the incredibly successful theory that describes these specific interactions between matter and light, including these vacuum effects, is called Quantum Electrodynamics, QED.
QED. Okay, so one source of the jitter is this unavoidable interaction with a quantum vacuum, mediated by virtual particles. Describe a QED. That's one layer.
A key layer.
But what about atoms that have more than one electron? Like most atoms. Those electrons aren't just sitting in separate bubbles, are they? They must interact with each other, too.
Absolutely. You add more electrons, you add another crucial factor. Electrons, carry a negative charge.
And like charges repel.
Exactly. They are inherently antisocial, you could say, constantly trying to avoid being too close to each other.
Like trying to shove the negative ends of two magnets together, they push away.
That's a pretty good analogy, yeah. They are in continuous motion relative to each other, engaged in this really intricate dance. Their positions are always shifting as they navigate this mutual repulsion.
And that constant shuffling around, that affects the atom's total energy.
It certainly does. The electrostatic potential energy between the electrons depends directly on their relative positions.
Which are always changing.
Precisely. Since their positions are constantly changing due to this correlated movement, they're dodging each other while also obeying the quantum rules. The total potential energy of the electron cloud fluctuates rapidly.
Yep.
Understanding this dynamic inter-electron interaction is, well, it's essential to grasping the full picture of the atom's electronic structure and its whole energy landscape.
So it's like a double whammy. You've got the quantum vacuum interaction and the electron repulsion, both contributing to this continuous energy jitter within the cloud.
Both are fundamental aspects, yes.
But, okay, if this is all happening at this invisible quantum level with virtual particles and fuzzy clouds and constant dodging, how do we even know these fluctuations are real? Can we actually see their effects or measure them?
Now we get to the proof. This is where the rubber meets the road, experimentally speaking.
Good.
These fluctuations aren't just neat theoretical ideas, they have distinct measurable consequences. In fact, they provide some of the most powerful experimental evidence we have supporting quantum theory, especially QED.
Really? Okay, I'm intrigued. What's the first piece of evidence our sources highlight?
The Lamb shift. This is a landmark discovery in physics.
The Lamb shift.
Yeah. So, early, simpler quantum theory predicted that certain energy levels in the hydrogen atom, specifically states called the 2s1/2 and 2p1/2, should have exactly the same energy.
They should be identical energetically. Degenerate is the term.
Degenerate, yes. That was the prediction.
But nature had other plans.
Nature had other plans. In 1947, Willis Lamb and Robert Rutherford did these incredibly precise experiments using microwave spectroscopy.
Okay.
And they found a tiny but definite energy difference between these two states. A minute split where the existing theory said there should be absolutely none.
Wow. And that tiny gap,
Mm-hmm.
that difference in energy, you're saying it's caused by the electron interacting with the quantum vacuum's fluctuations.
It is. That's the explanation. And this is where the deep insight comes in. It showed that the vacuum isn't just passive empty space. It's an active participant, capable of subtly shifting the atom's fundamental energy levels.
How does the vacuum interaction create that specific split?
Okay, so the electron in that 2s state, because of its probabilistic quantum nature, actually spends more time very close to the nucleus compared to the electron in the 2p state.
Right. Different shaped clouds, sort of?
Sort of. Now, when that 2s electron is constantly being jostled, buffeted by these virtual photons from the vacuum, it effectively smears out its position just a little bit.
Smearing out its position, like it gets fuzzy.
A bit, yeah. And that slight smearing makes a difference because it subtly changes how the electron, on average, interacts with the electric field of the nucleus. That field is strongest right at the center, you see.
Okay.
This altered interaction slightly shifts the energy of the 2s level relative to the 2p level. The 2p level is less affected because the electron in that state spends less time near the nucleus anyway.
So the vacuum's jitter causes a slight blur in the electron's position, especially when it's near the nucleus, and that blur subtly changes its energy interaction with the nucleus, creating that tiny measured energy gap.
That's exactly it. And the truly remarkable part, the validation, was the quantitative agreement.
You mean the numbers matched?
Astonishingly well. The energy difference measured by Lamb and Rutherford matched the predictions made by QED calculations that specifically included the effects of these vacuum fluctuations with incredible accuracy. It was a massive triumph for the theory.
Wow. Okay, that's pretty compelling evidence. These fluctuations physically shift the energy levels within an atom. What other consequences do the sources bring up? I think I saw something about spontaneous emission mentioned.
Right, spontaneous emission. We all know that if you excite an atom, pump energy into it so it jumps to a higher energy state, it doesn't just stay there forever.
No, it falls back down.
It eventually drops down to a lower energy state, and when it does, it emits a photon, a particle of light.
And that's spontaneous emission. That's where light comes from, basically, like in neon signs or stars.
Fundamentally, yes. That process is the source of light in countless phenomena.
But the puzzle, classically at least, is why does it happen spontaneously? From a classical view, there's no inherent trigger. It seems like the atom just decides to emit the light at some random moment.
And that is the puzzle from a classical perspective. There's no obvious cause for the effect of emission. But quantum mechanics, specifically QED and vacuum fluctuations, provides the trigger.
The vacuum again.
The vacuum again. Remember those virtual photons constantly popping in and out of existence in the vacuum?
Yeah, the froth.
They are the key. These virtual photons interact with the excited electron in the atom. This interaction essentially stimulates or nudges the electron to make the transition down to a lower energy state.
So the virtual photon gives it a push.
Kind of. And in making that transition, the atom releases its excess energy as a real photon, the light that we actually see.
So what looks like a completely random, spontaneous event from our perspective is actually being prompted or triggered by the underlying quantum activity of the vacuum itself.
Precisely. The spontaneous decay isn't truly uncaused. It's triggered by the vacuum's inherent jitter. Without the quantum vacuum and its fluctuations, excited atoms wouldn't spontaneously emit light the way they do.
That completely flips the classical picture on its head.
That's amazing.
Okay, so fluctuations affect single atoms, their energy levels, how they emit light. Do these effects extend between atoms? Like, do they influence how molecules interact or why matter sticks together?
They absolutely do. This leads us directly into understanding a whole class of intermolecular forces, the van der Waals forces, specifically the type known as London dispersion forces.
Right. I remember those from chemistry.
Yeah.
The weak attractions between things like non-polar molecules, the ones that explain why even gases like nitrogen or helium can eventually condense into liquids if you cool them enough.
That's exactly the one. Think about a non-polar atom like helium. On average, its electron cloud is perfectly symmetrical around the nucleus, no positive or negative end. But because the electrons are constantly in motion, and because their positions are fluctuating, probabilistically remember that jitter. At any given instant, the electron distribution probably won't be perfectly even.
So just for a fleeting moment, it might be a bit lopsided.
Exactly. You get a temporary fleeting imbalance of charge. One side of the atom might momentarily be slightly more negative, the other side slightly more positive. It creates a tiny, instantaneous electric dipole.
Like a tiny temporary magnet that just flickers into existence.
That's a good way to think about it, a fleeting, instantaneous dipole. Now here's the crucial part. If another nonpolar atom is nearby.
Yeah.
This temporary dipole in the first atom can influence the electron cloud in the second atom. Its fleeting positive side can attract the electrons in the neighbor, and its negative side can repel them.
So it induces a similar lopsidedness in the neighbor.
Precisely. It induces a corresponding synchronized temporary dipole in the neighboring atom. The slightly negative side of the first atom attracts the slightly positive side of the induced dipole in the second, and vice versa.
And that creates a momentary attraction between them.
A weak but ever-present attractive force between the atoms or molecules.
Wow. So the inherent quantum jitter, the random motion of electrons, and maybe even those vacuum interactions within one atom, creates a temporary unevenness, which then induces a matching unevenness in a neighbor. And they get this temporary little pull towards each other.
That's the core idea of London dispersion forces. And these forces, born directly from the synchronized probabilistic fluctuations of electron clouds between neighboring atoms, are absolutely fundamental.
They sound weak, though. Temporary, fleeting.
Individually, they are weak and very short range, but add up over countless atoms in a substance.
They become significant.
Very significant. They are the reason nonpolar gases like nitrogen and oxygen condense into liquids at low temperatures. They dictate the structure of many molecular solids, like dry ice. They play crucial roles in biology, like helping hold the strands of DNA together, and even in things like how geckos can stick to walls.
Gecko sticking to walls comes down to this quantum fluctuation.
In large part, yes. The van der Waals forces between the tiny hairs on their feet and the surface are dominated by these dispersion forces.
That's incredible. So from tiny shifts in atomic energy levels, like the Lamb shift, and the very reason atoms emit light spontaneously,
Right.
all the way up to explaining the bulk properties of matter around us, like why gases condense or how molecules stick together, even geckos. The seemingly subtle energy fluctuations of the electron cloud are absolutely critical.
Absolutely critical. What's truly remarkable, I think, is seeing how these microscopic quantum effects, these unavoidable jitters stemming from uncertainty and the vacuum, scale up to produce tangible macroscopic forces and phenomena that we observe and experience every single day.
Okay, so let's try and sum this up. That old solar system model of the atom, useful starting point, but really limited.
Very limited.
The reality is this probabilistic electron cloud whose energy isn't static. It's fundamentally dynamic, constantly fluctuating, jittering.
It's a reflection of the inherently vibrant and, well, uncertain nature of the quantum world. The atom is constantly interacting with its environment, and that includes the vacuum itself, which isn't empty at all.
And the evidence, the fingerprints of this jitter, they're all around us.
Definitely.
The precise colors of light atoms emit shifted by the Lamb effect, the fact they emit light spontaneously in the first place, triggered by the vacuum. And even the forces that allow matter to condense or stick together, these van der Waals forces.
All stemming from those fluctuations. Our sources make a really compelling case, I think, that this reveals a vibrant and energetic reality that lies beneath the surface of the observable world.
Yeah, the vacuum isn't empty, and even seemingly static matter isn't truly static at its most fundamental level.
It's constantly humming with this quantum activity.
It really does make you pause and think, doesn't it? If this constant invisible quantum fluctuation is responsible for these fundamental things, energy levels, light emission, intermolecular forces, what other subtle ways might this fundamental jitter be influencing the universe we see? How deeply connected is seemingly solid, stable matter to that dynamic quantum vacuum? There's a whole different way of looking at what exists, you know?
It certainly challenges our everyday intuitions about solidness and emptiness. A lot to ponder there.